All right, for class 14/15, this is example 6-7 out of Norton, doing velocity analysis with a 4-bar mechanism. And just to review here, it's 100 millimeters distance between the base right here, between these 2 points, 40 millimeter crank at L2, aka A. A lot of times we'll call that link 2. Link 3 is 120 millimeters. We call that B. And then link 4 is 80 millimeters. We'll call that C. They're saying at the this position right here, that's going to be theta 2 is equal to 40 degrees, and that omega 2 is, so that's in this direction right there, because it's positive, is 25 radians per second. And we want to, the things that we do first, if this was a regular problem, is we do the position analysis first and find that theta 3 right here was 20.3 degrees, and theta 4 was 57.3. So what would really be good is if we were to take a look and see what this looked like. All right, so I think these are going to be under, well, actually I think they are under this assignment right here, and I had to close it down. So these were examples that I did for homework 5 right here. So here was the homework, and you can see, actually, I think I accidentally made this into the 360 version of this when I was doing a video. But right here was the remainder of it, and that was the 100, 40, 120, and 80. And then you could see that this is the 40 degrees. Yes. So this is the configuration right here, this orange one that you see over on the right-hand side. And I got rid of the crossed configuration, but you could see that this right here, it was actually being theta 2 and theta 3 2 and theta 4 2. That actually turned out to be the open condition right here. So this is what the thing would look like right here, and we're going to make this thing go counterclockwise. So the velocity right here we could expect to go in that direction. Oh, and by the way, if we were going to use if we were going to try to figure out what the direction of everything, one method that we could use is to take the ICR, right, where we extend that length and we extend the length off of that link right there, and we see that if this velocity that we have right here is in that direction, then that means that this omega is coming there. So that's going to be omega 3, right? And this right here was omega 2. And if that's the case right here, then this velocity right here, so it has to be, which actually turns out to be the velocity of point B. And that means that this guy, omega 4, has to be in that direction that we can anticipate. And let me get rid of all this junk because I'm on autosave, and it's going to save all that junk right in there. So that's what we're going to find. By the way, this is something what you see on the screen here is what we're going to do soon with this for the homework, and I'm going to cover that in another part of this video. Okay, so moving back to this example, I already covered this actually last night in class. But so one thing we might want to do is like summarize some of this information that was presented to us. This was going to be 40 degrees, and omega 2 was equal to 25 radians per second, and theta 3 is equal to 20.3, and theta 4 was equal to 57.33, And remember that getting theta 3 and theta 4 was not a pleasant experience. It was a long, drawn-out process. To get omega 3, we just apply A omega 2 over B times the sine of theta 4 minus theta 2 divided by the sine of theta 3 minus theta 4, which ends up being 40, 25, 120, right? And the sine of 57.33 minus 40 divided by the sine of 20.30 minus 57.33. And that's going to end up equaling minus. By the way, take special note that this guy right there is going to be end up being a negative number, and that's why we got a negative number, 4.122 radians per second. So therefore, that's going to mean that this one is going to be clockwise, and we just figured that out, right, from our configuration. This, of course, is a generic one right here. We actually looked at the actual configuration in that Excel spreadsheet, but we know that this velocity VA right here has to be in that direction. Therefore, from that ICR, we had omega 3, and of course, it confirms that it is clockwise. While we're here, we might want to also go and say that we have VB right here, and that's going to predict that we have omega 4 right there. And that omega 4 is going to be equal to A times omega 2 over C times the sine of theta 2 minus theta 3 divided by the sine of theta 4 minus theta 3. And by the way, when going through the derivation, I alluded to it, and I wish I had actually worked it out and to demonstrate what the algebra was, that we needed to use a trig identity to get that sine of theta 3 minus theta 4, or any of the theta versus thetas. That was actually a trig identity that allowed us to do that as part of the algebra and to simplify the thing. Not equals. So in this one we have the sine of 40 minus the sine of not the sine of it, but this difference between the sine of the difference between those two angles, and then the sine of 57.33 minus our 20.3. Whoops. So you can see that neither of these is going to be a negative number, and we end up with a positive 6.998 radians per second. And in many dynamics problems that we might have experienced before, that's like the first step quite often when we're doing the rigid body velocity. We want to find those omegas. It's often the very first thing that we do. And we usually do it so that we can find what the velocities are. So we really would like to find VA and VB. And while we're at it, it would be good to have VB with respect to A, right? Because that was actually the original equation, if you recall. That's what we got from from doing the method of the method of using the complex notation. Remember that we got A omega 2 J e to the J theta 2 plus B omega 3 J e to the J theta 3 minus C omega 4 J to the E J theta 4 was equal to 0. And then these parts, this right here was VA. This right here is VB. right? Because you would get this VB if you had omega 4 times the radius, c, right? C is the dimension. It's c times omega 4 is equal to VB up here. And a times omega 2 is VA. So that, because we know that, whoops, I keep doing that. So hopefully this will come back up. Yeah, see, what I've done is I've activated the pan slash, let's see, click it on again. We know that VB with respect to A is equal to VB minus VA. That's just the definition, or that's just what the statement is of B with respect to A. So that we usually calculate and we say that VB, well, we could just rewrite that down for what's below down here, right? That this is VB with respect to A. Because what we can write is VB is equal to VA plus VB with respect to A. And remember from dynamics, what that is really describing is the motion of that linkage right there, of the coupler. That the coupler is in the 3 diagram method, right? And maybe I'll put it down here and then I'll delete it. The 3 diagram method of the coupler says that we know VA and we know VB. What I'm trying to do here is trying to connect this back to what we learned in dynamics. That is, if you learned this method. So we're taking VA as the reference, so we place it in both spots. Let me put in use a couple other colors here. Because I have the colors, might as well use them right here. Here you go. I'll pick one. So VA was kind of like upwards that way, but VB was like a little bit more that way. Right in there, and so we could place in this VA in both of them, right? That's supposed to be both be parallel right there. It's supposed to be both VA right there, and then we pin it at VA at A, and then we have perpendicular to it. We have a the motion, and we find that this goes right here. And then we have VB with respect to A, right? So that's going to be, actually, I'm sorry. It's this guy right here, right? It's that direction. So that becomes omega 3, and that is VB with respect to A, right? So that right there is describing in the 3 diagram method the motion of the coupler. But here in this method, we have written it out as this complex notation that's presented right up here. So if we want to get these the values right here of the VA, all we have to do is take A omega 2 J E J theta 2. We plug in the values for this. And I did this in class last night. And we say that it's going to be 40 times 25. And then we replace for the E, well, actually we replace for both the J, we take this is just one simple shortcut. For the J times E J theta 2, we take J times the Euler identity. So we've already went ahead and went J times J, so that makes it the negative sign of the 40 degrees right here, plus J times cosine of 40 degrees, right? And if we do that and work the thing out, we get negative 642.8 plus J times 766.0, and that's going to be millimeters per second. If we work out the sum of the square root of the sum of the squares here, we get the 1,000 millimeters per second, which makes sense because it was just 40 times 25, and we could have got that. From the angle, that's going to be, we end up with, we take the inverse tangent, we get 50, which makes sense because it was this was equal to 40, so it kind of makes sense that this right here is going to be equal to 50 right in there. Okay, because this right here would be equal to 40. I think that's correct. Yeah. And then we have VB is going to be equal to C. Let me change colors here because I can. VB is going to be equal to C omega 4 J e to the J theta 4. Or if we put values into this, that's going to be 80 times, and then, yes, we found up here, we found the 6.998 for omega 4, and it's going to be times negatives the sine, and then we need to use 57.33, and then plus J cosine of 57.33. If we work out the values here, we get negative 471.3 plus J times the 302.2 millimeters per second. And then we could find the magnitude of 559.8 millimeters per second. And we would also find that it has an angle of 32.67 degrees, which actually will probably be our just the complement of 57.33, you'll notice. And then lastly, if we take the velocity of B with respect to A, we're going to use that B omega 3 times J e to the J theta 3, and that ends up being 120 times our negative 4.122 negative sine of 20.30 plus J times the cosine of 20.30. Right, and if we work that out, we end up finding B with respect to A is going to be equal to 171.6 minus J 463.9 millimeters per second, which we would equate to being 494.5 millimeters per second, and that's going to be downwards of 69.7 degrees, and we know that it's going to be down in that quadrant because it's a negative y and it's a positive x. We could have also found VB with respect to A by just taking VB and subtracting VA from it right here. So if we go back to the values that we got in here, that would be this minus that, right? And so you see we get 471.3, negative 471.3 minus 642.8. We would end up with a 171.6. And if we had through, you go right here, 302.2, and we subtract out 766, we get a negative 463.9. So that just shows the trying to tie things together. I know this is an example out of the book. You can take a look at what they see here, but I'm also trying to tie it back into what we had in dynamics. So what we want to do as part of this, all right, so I guess I'll keep it and I'll delete all this stuff later. if we were to do a velocity analysis of this right here, and I guess I'll go up to my chapter 6 problems, doing a velocity analysis of this. Let's see, that is this. This is example 6-7 out of the book. I end up getting the same thing, right? I show this one is, I did this for myself just to arrange everything. And here's my omega 3 and my omega 4. And then from here, I find what my Vx is, and I find my Vy. And then I find my magnitude, and then I'm able to get what my angles are going to be of this. And and I think, by the way, I think I'm doing both configurations. No, I'm not quite sure why I have that angle right there. Oh, okay. And then I have I'm able to do these other two. But let's see. Do I do this? Is these two things combined? No, I'm trying to think of which way that I was going to have. Okay, here's for the full rotation. Here's what I do for my full rotation now. You've seen before where I have, in a separate video, I went and I combined these together. All right, so in that separate video, let me see, do I have this right in here? No, it's right in here. Okay, so in a separate video, I got to this point right in here. So let me copy this one, and so this is the same thing. This, by the way, this is the result. So you need to take a look at class 8 where we have the video for the full rotation, and I also made a coupler curve right up here out of this. So I want to make a copy of this before, so I don't have to, so I don't mess the thing up. And what I want to try to find are, well, I can find a bunch of different things. Okay, so firstly, I might modify this a bit. Let me switch orientations here on my computer. So I'm detaching and flipping this over to turn it back into a laptop instead of a tablet. So it's much harder to use in that configuration. And how long is my video so far? It's already 22 minutes. Okay, so maybe I want to make a separate video of this, because anything 22 minutes is a long time to have watched that. So that's just walking through the example. Let me make a separate video where I talk about turning this into an Excel spreadsheet. So I'll be done here. Done.